Hello everyone, in this video I'll talk about the local level model. My source for this video is the book Time Series Analysis by State Space Methods by Darwin and Koopman, so if you want to know more, check the book out and you'll find more informations, both about the local level model and about other topics. First of all, I want to define what a state space model is. A state space model is a model which describes the development of a system over time. The system in question depends on an unobserved sequence of vectors, we call them state vectors, alpha t, associated with a set of observations, yt. This may seem complicated, but it's really easy, and I'll show you with an example. Imagine that we have two lights which change color over time. The first light can be red or green, while the second line can be pink or light blue. Our lights change their colors randomly every 2 seconds. The vector containing the colors of the two lights at time t is our state vector for this case, and our state vector is upgraded every 2 seconds. We call state space the set of all possible values that the state vector can take over time. We collect a series of photographs which only eventually reflect the real colors of our lights. We want to be able to say something, even if our photos, our series, our observations aren't really reflecting the real colors. So this is a really simple example, but it makes clear which kind of problem we are dealing with. We have some observations and we have a state which changes over time, and our observations have disturbances, but we are interested in the development of the states. So the local level model is just a simple state space model. In this model, the states and observations are one-dimensional. The first equation, called observation equation, describes the relationship between the state vector and the observations. We notice that in the local level model, the observations and the states differ only by a random disturbance. The second equation, called state equation, describes the evolution of the state vectors over time. In the local level model, the new state is equal to the previous state plus a random disturbance. We assume that the first state has a known Gaussian distribution with mean A1 and variance P1, and that the disturbances are normally distributed at each time with mean 0 and variance is sigma squared epsilon and sigma squared eta. Also, we assume that all disturbances are pairwise independent and that they are independent from A1. Of course, if you're already familiar with time series, you may have noticed that the state equation is a Markov process and a random walk. Now, given all these assumptions and the theorem about the sum of independent Gaussians, we can conclude that yn, our vector of observations inside the model, this is a theoretical vector of observations, it's not an actual sample, is distributed as a multivariate Gaussian with mean A1 and variance omega. I won't include in this video details about omega, but you can find details in the book. This distribution implies that, given a time series, we could potentially estimate the parameters sigma eta and sigma epsilon through classical statistical inference. But is it good enough to use classical statistical inference? First, if our observation vector gets periodically updated, we should repeat all the calculation and all the optimizations every time, which is very time consuming. And second, if we represent our model in a single equation as shown on screen, we notice that our variables are highly correlated. This means that maximum likelihood estimation gets increasingly complicated as n increases due to all the conditional probabilities that we have to account for. How do we solve these problems? I'll show you how we solve these problems in the next video, and the solution will be the Kalman filter, and we'll develop the Kalman filter for the local level model. Thanks for watching and goodbye.